Hello everyone, we're going to look at Amperes Law today. Amperes Law is very similar to Gauss's Law. I know you all remember Gauss's Law. There it is. Alright, so here we would pick a Gaussian surface to mimic the shape of the object, or it's supposed to say surface, or the shape of the magnetic field. So for Gauss's law, if we had a positive charge, that would radiate field outward. We'd pick a Gaussian surface so that the field would always be perpendicular to the surface, and that means the normal to that surface was always parallel, making the dot product 1. Right? So if we're looking for the electric field, the area of our Gaussian surface, since that's a sphere, is 4 pi r squared. Here we're enclosing the total charge, we'll call it capital Q, and that would be over epsilon naught. And we've done this how many times, right? Alright, so Amperes' law is very similar. Here we're going to have, instead of a closed surface integral, we're going to have a closed loop integral of B dot ds. I should have put the vector signs over there. These are vectors. And it's going to be equal to mu naught times the I enclosed. All right, so it's very similar. Instead of using a Gaussian surface, we're going to use an Amperian loop. All right, so we'll have a wire, and maybe we'll have current going into the page. And if we use the second right-hand rule and point our thumb in the direction of the current, it will create a magnetic field. And the direction that your fingers curl, so here the field would be going clockwise. We will draw our Amperian loop that is at this distance that we want to know the strength of the field. So our Amperian loop will follow the loop of the magnetic field. Since the magnetic field is always tangent, we're going to make the direction of our Amperian loop in the same direction as the field, making this dot product 1. And if we could do this right here, Amperes' law is no different. So B dot the length of the Amperian loop, which is just 2 pi r circumference, is equal to mu naught, and we're enclosing all of the current. Call that a capital I. And solving for the field, mu naught I over 2 pi r. And if we look at our proof from Biot-Savart, you'll see that we got this for an infinite wire. So we're not going to use Biot-Savart for infinite wires. We're going to use Amperes' law, just like we don't want to use regular integration for point charges or anything long wires for Gauss's law. This is used outside of a long straight wire, but only outside. If we are inside the wire, it still behaves a lot like Gauss's law, but those are the hard problems with uniform charge distribution. So let's look at one of those. All right, so here would be a wire, and we're really zooming in on here, so we have current going into the page again, and it's evenly distributed throughout the wire, so it's not there's not more current towards the center or the outside. It's all the same. So I tried to do that with my little X's so that they're evenly spaced as best as I can. All right, so green is the current going into the page. We want to figure out what the magnetic field is at some distance Let me change this radius to capital R. We want to figure out what the magnetic field is at some distance R away when it's inside of the radius of the wire. All right, so if the current is going into the page, we have a magnetic field that is going to be clockwise again. This is starting to look a little bit jumbled here. Okay, so we're going to draw an Amperian loop. At that distance R, and we're going to have our Amperian loop vector point in the same direction as the field. All right, so we have a uniform charge density, and that charge density is going to be for a cross-section. So a cross-sectional area is going to be the total current, or the current enclosed, divided by the area of the Amperian loop, and that'll equal the total current I throughout the entire wire divided by the area of the wire. So to figure out the I enclosed, we just have to multiply the total current by the ratio of the area of the loop by the area of the wire. So total current must be capital I. All right, the area of the loop is going to be pi little r squared. The area of the wire is going to be pi capital R squared times I. So we get pi's cancel, but now we know what the total current enclosed is going to be. So now we can go to our Amperes law. I'm going to come over here. So we have B dot ds, where our Amperian loop length is 2 pi little r. It's going to be equal to mu naught times that ratio of I times r squared over capital R squared. Solving for B, we can see one of these R is going to cancel one of those. So we end up with mu naught I over 2 pi capital R squared multiplied by that variable R. All right. So this is a linear relationship, right? All of this is constant. As we move further and further away from the center, the magnetic field increases linearly. All right. So our field strength outside of the wire was a 1 over r relationship. So it was mu naught I over 2 pi little r. All right. So if we were to draw the graph of this, let's use green. Magnetic field strength as a function of r, we will increase linearly until we hit the radius of the wire, and then drop off as a 1 over r relationship. So those ones aren't too bad. We are going to look at one where we have a non-uniform charge distribution in the wire, And it's a little tougher because we have to do an integration just to figure out the current enclosed. So you'll see that in the next video.